So working on the twin primes conjecture, found tons of patterns. I have like a set of rules over here, prime number rules, things that I've discovered, which a lot of it has already been discovered. Like people have already caught on to certain patterns, like the 1379 pattern, and then the 2468 intervals. Which, if I'm right, recently I saw the 10 and 12. So let me add that. 10 and 12. So I'll look further into that later on. But you get the idea that it's like, the intervals as in two, twin primes, right? They're spaced, the primes are spaced out by 2, by 4, by 6, by 8, all that stuff. But if I'm right, there's 10 and 12. And there's some that are like even bigger numbers, but I'm just pointing out that so far, the intervals are currently in even numbers, 2, 4, 6, 8, 10, 12, 14, 16, and the list goes on. So you get that idea. So, because the primes, you gotta remember, are except for 2, all the primes so far are odd numbers. So, so that means the even numbers are obviously excluded. But the fact that the intervals, like what separates the odd numbers from each other, or the odd primes from each other, just so happen to be even numbers, 2, 4, 6, 8, so on and so forth. So there's a pattern there. So even though primes might seem random, it's not really random. It's just that it literally has a set of rules, certain patterns. Because for example, primes being odd, obviously that means they're not going to be even. Since they're not even, right? Something has to be even, right? So the fact that you have primes separated by 2, 4, 6, 8 spaces, right? Digits, numbers, units, whatever you want to call it, right? That makes sense, right? Because it's like everything's either odd or even, as well, right? Everything is either yes or no, one or two, on and off, and so forth and so forth. So there has to be a balance, which is the whole point. Because saying random means there's no balance, right? There's no structure. There's no give and take, as it were. It's just everything's just chaotic. It's like, no, there's no chaos in primes. There is a pattern. There's a uniform. There's rules. That's the whole point. It's trying to figure it out, right? So we're trying to figure out what are the rules, and I found a good amount of them, as well as think about the twin prime conjecture, for example. There's other ones besides the twin prime, but because first, in order for you to try to figure out, try to solve the twin prime conjecture, you got to understand it. And it was a little hard to understand, considering the fact that not many people could really explain it. But they couldn't explain what I'm saying is they couldn't explain what would it take, right, for it to be proven, right? What do you need to see? What should somebody present that is the proof of the twin prime conjecture? Tons of people have done brute force and found tons of twin primes up to like really high numbers, which so far, as big as those numbers were, the conjecture has held true within that range. So logically, right, common sense, it should keep holding true, right? We've seen time and time again, that there are patterns, right? There are repetition. Things happen over again. If it happens once, it can happen more than once. It's just a matter of figuring out how many times it happens more than once, as opposed to will it happen more than once. So far, with all different types of math, right? All different types of anything, not just even math, just in life in general, we've seen things repeat itself, right? So to think that twin prime conjecture doesn't infinitely repeat. It's foolish, right? It's foolish to think it doesn't. Now, it's okay to be open, to think that maybe it doesn't under certain conditions. So the point is no one has pointed out what's that condition. What would cause it to not be infinite, right? So I started thinking, like, so what people want, in order to figure out the twin prime conjecture, is they want to know when what am I saying? Want to know why the twin prime conjecture is true, right? Like, why does it exist? Like, why are there twin primes? That's what I'm trying to say. Why are there twin primes, right? If you can figure out why twin primes happen in the first place, that because it's irrelevant if there's infinite of them, right? That part would be hard to prove, right? It'd be hard to prove this infinite amount of them just by trying to find the biggest number, because it always sounds like people expect you to find a number that proves that it's that the twin prime conjecture is true. It's like, but that's nearly impossible, because the idea is we're going from 0 to infinity. The idea of infinite is that it never stops. Since there's no n, right? There's no finite. There's no n. You can't, reach it, right? Since you can't reach the n, you can't fully be able to be like, all right, I looked at the entirety of infinity and I can see and I can show that at the end, there's twin primes there. Since there's twin primes there at the end, there's twin primes at the beginning, there's even twin primes in the middle. Clearly, there's infinite twin primes. Since we can't do that and grab all of infinity and show that, obviously what we need to show is, why do twin primes exist in the first place? Why does it happen? What makes them twin primes in the first place? Once you understand what a twin prime is in its most basic form, then that by default is like, oh yeah, of course there's infinite twin primes, because of this reason, because of this rule, right? Because the idea is we're trying to figure out what are the rules that govern the primes in general. Why are the primes odd, right? Except for 2. Why are the primes? Why are some certain primes only separated by 2? Why are some separated by 4, 6, 8, and the list goes on, right? Why? What's the pattern? What's going on there? So the thing I had started doing today, the most recent theory or idea I had, or something, or pattern that I've noticed and I started playing around with, is this idea. So you see the number 2 on the top. I put 1 plus 1. 1 plus 1 equals 2, right? Then 3. 1 plus 2 equals 3. Notice that 1, of course, is smaller than 2 by 1. Smaller by 1. So it's 1 plus 2 is 3. 5 is 2 plus 3. Right? It's 2 plus 3. So 2 and 3 is bigger than 2 by 1. So you notice that, right? 7 is 3 plus 4. That's 7. And 4 is bigger than 3 by 1. Notice that basic pattern. So you see 1, 2, 3, 4. Then you keep looking. 5, 6, 7, 8, 9, 10, 11, 12. But you notice 13 is missing. Then we go to 14, 15, 16, 17 is missing. 18, 19, 20, 21, 22, 23, 24, 25 is missing. 26, 27, 28 is missing. 29, 30, 31, 32 is missing. 33, 34, 35, 36, 37. And that's how far as I got. So from 1 to 37, right? And there's a couple numbers missing. But you notice the numbers that are twin primes, they share a number. You notice the 3 and the 5, they both have 2 in their equation. You notice the 5 and the 7 have 3 in their equations. You notice the 11 and 13, they both share 6. 17 and 19 share 9. But you notice, 23 and 29 don't share a number. And 13, is missing. Ironically, right here, it would have been 12, 13, like 12 plus 13, which is 25, right? But you see, it's not there. It's not a prime. So 13 is missing there. So 13 plus 14, right? Or did I say it right? No, 12 plus 14 is what I'm trying to say. 12 plus 14 is missing. But as you can see, the 29 and 31, which are twin primes, notice they both share 15. 41 and 43 are twin primes that share the 21. 59 and 61 share 30. 71 and 73, they share 36. So you see there's a pattern, especially for the twin primes. You see there's a pattern. Twin primes actually share a number that, is part of what makes them twin primes. So now we're getting into the basics, right, of twin primes. The fact that they do, not only are they separated by 2, they literally share a number. And then the most important thing is sequence. It's in an order. 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 right? There's an order. So slowly what I've been working on is breaking down bit by bit, pieces by pieces. Like right here, as you can see, I got my list of primes and stuff like that, and I've been doing the interval of 10. Soon I'll be experimenting with intervals of 12 or power of 12, whatever you want to call it. But I've been using 10, so 10, 20, 30, 40, 50, all the way, up to 1,000, right? So I got all the way down here to 1,000, right? So I got a little bit more than that, but I'm down to 1,000, which is what I've basically been working with. Down to 1,000, so I got all the primes from between 0 and 1,000. I have all the primes there. There's some times where the primes skip. So you see these things where I'm saying skip, where there's no prime. So between 510 and 520, within that range, there are no primes. So there are times where primes don't exist. Since they don't exist, obviously twin primes would not be in there because there's no primes in there. Right? So then makes you want to okay, primes sometimes don't exist. Within a certain range. Why is there gaps, right? So as you can see from my paperwork right here, 200 right here, between 200 and 210, it skips, right? So there's no primes there. Then over here, 320, no primes. Over here, 510, no primes. 530, no primes. 620, no primes. Right? So it makes you wonder what's going on there. 840, no primes. 890, no primes. So that's obviously something I have to look into. 1070, 1130, 1140, no. So, stuff like that. Trying to figure out why. Another thing with the pattern, let me minimize that. Minimize these with these, and these are screenshots of that pattern. You see, I started adding I started connecting the twin primes. So all these red lines are numbers that are twin primes. They're only separated from each other by 2, right? So 3 and 5 are separated by 2, 5 and 7 separated by 2, and so on and so forth. So you see, these are all the twin primes. And you see, how close they are and pattern-wise, how very similar they are. Because you see how here, you go from 29 to 31. Right, so notice that the second number is 9, and the second number on this number is 1. 9, 1. Over here, 59 and 61, the second number is 9 and 1. So the pattern is not just like up here where it says 1, 3, 7. 1, 3, and 7, 9 are prime numbers. There's also 9, 1, which I have to correct that, add that detail. 9-1 is another arrangement. So basically, it loops around, because you notice the 1 is right here and the 9 is over here. So it goes from 9 to 1. So it loops around. That's an important thing, right? Loop, right? Infinity. So it loops around. So that's an important detail. Something recently I noticed. I'm like, oh yeah, 9-1. It loops around. And then you see right here, 1, 3, right? 1 and 3, 7, 9, right? Right here is 7, 9. Right here is 9, then it goes back to 1. So 149 to 151. So it goes from 9 to 1. So that's what I look. I also look at the prime numbers as for their individual numbers, like 151, for example. Those are 3 individual numbers, right? 1, 5, and 1. Those are individual numbers. It's very important. So many things. I'm not going to go through all the rules, but because there's still some that I'm working on fine-tuning, but you get the idea. Let me go through here first. So here you see a lot of red lines. Here you see less, and here you see very less, right? So you see less than here. So here's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 primes in this column. 1, 2, 3, 4, 5, 6. So there's only 6 here. So 6 here, 8 here, and 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there's 20 there's 20 twin primes here. There's 8 here, and there's 6 here. All right, so 20, 8, and 6. So far, and this is from 0 to 1,000. So we gotta keep that in mind. 0 to 1,000. So the first 1,000 numbers within that range, you have 28 and 6 twin primes. So that's 28, 20, 30, 34. That's 34 twin primes. Within the first 1,000 numbers, there's 34 twin primes. So that's an important detail. Double checking stuff. Alright, so that's an important detail. So it's so what it looks like, for time, there's starting to be a lot less. Right? You start noticing there's a lot less. And when I play around and make a couple more of these and go further, go up to 2,000, see what goes on, what happens there, and so forth and so forth. Now I know there's more twin primes beyond this. It's just that I noticed, just point out this pattern. There's a lot here at the beginning, but then it slowly starts going down. But then if I'm right, it'll go right back up. I'm after 1,000. So after 1,000, the twin primes start popping up again. And then I heard, the idea that after a while, primes started being very scarce. So it's gonna, primes. There's gonna be a lot of skip, right? A lot of number ranges just gonna skip. I might end up skipping like 1,000, 2,000, 3,000. So makes you wonder why. And of course, I need to get to that point to find out why, because it's just something I heard. I haven't seen it myself. Primes, just completely utterly dropping off, consistent, like back to back. I haven't seen a roll where I'm just putting skip, right? I do have a good considerable amount of skips in here. Let's say there's like 10 skips. All right, so there's 10 skips there, but I haven't seen like a full range of let's say 2,000 to 3,000 within that number range. There's no primes in there. I haven't seen that yet. Maybe they meant twin primes become more scarce later on in bigger numbers. Not that primes in general become, but I'm pretty sure they said prime in general. But I'll find out later on. So I guess we won't need these anymore. Just wanted to showcase that concept right there, that idea. So see, going to some of the rules. I just want to, document some of my ideas. This is just to help, why not share, right? Share this information, share these ideas, because it could help other people. There's a possibility a lot of these have already been found. Other people already know about this, about these things, these patterns. But that's the thing, is like I don't see a lot of information about it. Like I'm looking at videos of twin prime conjectures, and usually they just spend time trying to explain the conjecture and that it's unsolved, but never show any. They barely show any, rules, as it were, right? Stuff like this, like how I'm showing. Sorry, like how I'm showing, these patterns, because that's the thing, is like we're trying to find patterns, so I barely see them posting up patterns. Like for example, let's see, 38 plus 39. I've been using the calculator a little bit just to make my life a little bit easier. So 38 plus 39 gives us 77. So that's not the right number. So 39. Oh yeah, 39, 40. So that's what it should be, 39 and 40. 39 and 40 should give us 79. 39 plus 40. I mean, it's obviously 79. So you see right here, 38 was skipped. This is separated by 4, so clearly that's not a twin prime right there. 40 plus 40. 41, 40, yeah, 42. 41 plus 42 is 83. So there we go. They're separated. They're not twin primes. That's why they don't share a number. But they are in sequence, right? 39, 40, 41, 42. So they're in sequence. So you see, there's obviously there's a pattern. So there's a pattern. There's no randomness there, right? There's a pattern. I mean, you do still have something missing, which makes you wonder, okay, why is it missing? But that's the whole point, is to figure out, okay, why is it missing, right? Find the next pattern. What I've seen so far is that, when it comes to, when it comes to primes in general, is the fact that it's layers upon layers upon layers of rules. It's not just like one rule that applies to everything. There's not just one rule that applies to all the primes. There's multiples, right? For example, right? I'll start reading out my 11 rules that I have so far. I have more, but none of the prime numbers end in a 0. Right? None of the prime numbers end in a 0. All numbers that end in a 0 are tend to be even numbers, so they're not prime. So no prime number ends in 0. They all end in 1, 3, 7, 9. Except for 2 and 5, right? For all prime numbers tend to end with 1, 3, 7, 9. All twin primes tend to have, well, we'll get to that. That's close to the bottom. Anyway, all primes start with a number from 1 to 9, right? So they won't start with a 0. So whenever you look at a prime number, it'll start off with a 1. Right? Or 2 or 3 or 4 or 5, 6, 7, 8 or 9. But won't start with the number 0. So it won't be a 0, 1, 2, 1, right? It'll just be a 1, 2, 1. And since they don't end in 0, you will never see a number that starts with a 0 and ends with a 0, obviously, right? All prime numbers can have numbers from 0 to 9 in between the first and last number of the prime number. So prime numbers can have 0, but it will never be in the beginning or at the end of the number. It will always be in between. So it could be a 1, 0, 1, 0, 9, right? That's an example. Right? You can have, let's write it right here. You can have You won't have this 1 0. You won't have that. It's 0 1 0 9. You won't have that number, but you will have a 109, right? 09. You know, as long as it doesn't end in 0, so you can have 10,909. That could be a prime. You can have a 1 0 0 0 0 9, right? You can, because it starts with a 1, ends with a 9, or it could end with a 1. Right? And it can end with a 2. It can end with anything, but what it can't end with is just a 0. Because if it's 0, then it's not prime. So prime numbers have to end in a 1 or 1 through 9. Just like it has to start with a 1 through 9. So it could start off with a 9. Oops, with a 9. You know, and it could end with a 1. You know, it could end with a 2, all the way up to 9. So like I said, in between you can have other numbers, right? You can have 1, 2, 3, 4, 5, and then 9. Right? You can have any of, or you can have 0, of course. Let's just add 0. So you can have 0, 6, 6, 7, 8. Have all the numbers in there. So you can have something like that, right? Where you have all the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all between, you know, a number, whatever number it is, whether it's say 1, right, or all the way up to 9. Right? You can have that. So that's what all primes would be. So you see, there's a pattern. There's no randomness. If there was randomness, you know, you wouldn't have these pretty simple to understand and straightforward rules, right? Number 5, all prime numbers are mostly odd, you know, except for 2. That's an even number. 5 is obviously an odd number, but all the other numbers are obviously odd from what we've seen so far. Between every 10 unit number, between every 10 unit number, there is a minimum of, well, between every 10 units, between 10, you know, every 10 intervals, right? From 0 to 10, between 0 and 10, for example, you'll have from 0 to 4 primes, right? So you have no primes, right? That's 0, or you have 1 prime, or 2 primes, 3 primes, or 4 primes. That is about it, right? You won't have anything more than that. Actually, I already did look that up. You won't have anything more than that. So, and then when you have sometimes what I've seen, when you have 4 primes, especially if the 4 primes is in the 1, 3, 7, 9 arrangement, because if you have 4 primes, they're going to end 1, 3, 7, 9. Then I dub those double primes, because you literally have 2 twin primes, right? 1, 3 are separated by 2, 7, 9 is separated by 2, so there's that. Then we have 7. Think of the first number and last number of primes as borders of prime numbers. As the borders of the prime numbers. Yeah. The first number and the last number as the borders of the prime numbers. That's where you get the whole 0, 9 can be in between the 1s and 9. You know. So 8, there could be 0 primes in multiples of 10 numbers. Yeah, I already mentioned that. Or you could have 0. Obviously, these are some older rules. I know I updated these on a different copy of this notepad file, so to update these, but just wanted to share some of this stuff. But I know I updated these. Most of these don't say this anymore. I remember I also did mention 9 and 1, so let's update that. That's 9 and 1. Right, so let's just do that. So 1, 3, 7, 9, 9, 1. So let's update that. So, like I said, it goes around. It's 1, 3, 7, 9, and then it goes back. It goes from 9 to 1, so 9. And that's how twin primes are paired. They're paired in that arrangement, that order. So it won't be a 3 and a 1. Won't be a 9 and a 7. It'll be a 1, 3. Both numbers, both numbers be close to each other, and the first number will end at 1, and the second number will end at 3. And same goes for the next arrangement. The first number will end at 7. The second number of the twin prime will end at 9. But then there's a third version where the first number will be 9, and the last number will be 1. So that's the exception, right? The 9, 1 is an exception to the 1, 3, 7, 9 pattern, because it's just, like I said, it kind of circles around. So that's an interesting detail. That's something, pretty new. Well, for me anyway, from my little research, the fact that it does go around, it goes from 9 to 1. And for every prime number, there is 6 non-prime numbers, right? So, what is up to 6, right? That's why I said for every 4 prime numbers. So if you find 4 prime numbers in between, suppose we say in between intervals of 10, then that means there's 6 numbers that aren't prime. So between 0 and 10, for example, you'll find 4 primes in there. That means there's 6 that aren't. So 4 numbers are prime, 6 are not. So it's essentially to a certain degree, way of looking at it is for every. No, that wouldn't work. I was gonna say for every prime, there's 2 non-primes, but 4 times 2 is 8, not 6. Right? If you get the idea that if there's 4 primes, there's 6 that are not prime. And most primes have a reverse number prime number counterpart. For example, 13 counterparts is 31. I have to revisit that concept again, but I did notice that as a pattern. Let's see. Scroll here. So we said 13, right? So here's 13, and then over here is 31. So here's 17. So is there a 71? Oh yes, there is a 71. Okay. So here's 19. Is there a 91? Let's check. No, 91 is not, because 91 would be right here. So there is no 91. So, like I said, it was just an idea because it's something I noticed that it was there. So it was a pattern, but it immediately broke once you got to 19, right? But let's try 23. Is there a 32? Nope, 32. Let's try 29. Is there a 92? Oh, so you see that pattern already starts breaking down. 31 we know turns into 13. 37, is there 73? Which there is, yes. So it kind of, it stops and starts. So you see there's a pattern that starts and stops. So it's something. 41 turns to 14. There is no 14. 43 turns into 34. Is there 34? There's no 34. Is there a 74? No 74. Right here is there 35. There's no 35. 95. 95. 16. No 16. 76. There's no 76. 17. There is a 17. 37. There is a 37, which is right here. Right now. 98. There's no 98. 79. There is a 79 right here. So you see that a lot of them do correlate, a lot of them don't. So you see, so it makes it is so. In part of why I'm showing that is the idea of like, why do they show up? Why are most of these primes the reverse of the other prime? Right? Why are some of these primes? Why is 13 and 31 primes? Right? Why, Because remember, the arrangement of the numbers is you got the 1 before the 3, but in 31 you got the 3 before the 1, and they're both prime. Right? Why is that? But why is 29 and 92? Why is there no 92 prime? 29 is a prime, but 92 is not a prime. Why? So then it's just a matter of figuring out why. What separates them? What makes them fundamentally so different? They both consist of the same two types of numbers, which is the 2 and the 9. They're just arranged differently. One is in front of one comes before the other. So what fundamentally at a smaller level, right, separates them? So let's try to figure that out right now, right? Why not? That's what this is all about, math, right? So let's figure that out right now. Why is 29 prime but not 92? Right? So let's use this new little math method that I'm using, this little equation method. I guess I call it the equation method, where I use an equation to figure out why are they the same or separate. So 29, right? We already saw the 29 is 14 plus 9, 15, right? Plus 15. So we already have that. So what makes 92 92? What two numbers that are separate from each other by 1 that equals 92? Okay. So first off, half of 90 is 45, so that'll be our starting point. So 45, right, is 90, but we're trying to get to 2. So let's see, 45 plus 46 is going to give us 91, so that's not it. Let's try 46 and 47. So let's see, those, I think if I'm looking at it real quick, that's 93. So let's see, 46 plus 47, it is 93. Alright, 45 and 46, let's try that. 45 plus 46 is 91, right? 91, 93. So we can get 91, we can get 93. Double checking. We don't have neither 91, 93 as prime, and we definitely don't have 92 as prime. So 91, 92, and 93, all three of those are not prime. So there's that. But now we know. Alright, so we know that see, still thinking, give me a second. Because the idea is to have two numbers that are, again, separate by 1 that add up to the number, right? So 92, one way to get 92 would be, let's see, go back to 5. 245 is 90. See, because then you add the 2, right? Plus 2, that will get you 92. But you don't want to do that. Now, if we go back, now one way we can do it, of course, this is the way we can do it. 46 should be 92. The only thing is that it doesn't fit the pattern I was talking about, which was both numbers have to be separated by 1. So here, 46 plus 46 is 92. But because they're both the same number, right? And they're not separate. They're not separate from each other by 1. That's why they're not prime. Right? And let's try 45 plus 46, right? That gave us 40. That gave us 91. So even though that's separate, those are separate numbers. Those are the separate by 1. 91 is not a prime, so it makes you wonder, like, okay, why is 91 not a prime, even though it does fit the equation of two numbers separated by 1 that if you add them together, they add up to a number that you expect it to be a prime. So why isn't 91 a prime, right? But our goal was to see what separates 29 from 92. They're using the same they're using the same, units, right, digits, but you're getting separate, way separate numbers, right? Way separate. Let me see what else. Because logically, right, if we break down 29 into just a 2 and a 9, right, you will get a 4, 5, and then 2 will be a 1 plus 1, right? So 4 plus 5. So it'll be something like along those lines. And of course, we could arrange this a little bit different, but this is the only equation that will give us two numbers that are, in sequence, and they're separated by 1, right? They're in number order: 1, 2, 3, 4, 5, 6, 7, 8, all the way to infinity, right? 2 is one of the exceptions because you see 2 has the same number. That's why it's interesting about 2 is like, why is 2 a prime, even though it has both the numbers that you add together are the same number, while they're not separate by 1, right? Everything else is, right? Everything else that, all the primes so far, let's take this out. All the primes so far, change that, that are prime, right? So far from 0 all the way up to 83 that I did, they all fit that pattern of two numbers that are in sequence, in order, that are separate by 1. So 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 42, right? So here's some patterns that people can play around with and experiment, and hopefully y'all like this concept, like this way of viewing and looking at the prime numbers. Hopefully this can help some people out there just trying to know more about primes and twin prime conjecture. I'm not gonna keep talking. This should be enough, and of course I'll make future updated videos about this. That's the end of the video.